Welcome to the third episode of this series about Shannon's entropy, information, data, and knowledge. Although we all have an intuition about information, it can be quite difficult to understand and formalize the concept. If I were to ask you to define information, you would probably come up with something like facts provided or learned about something or someone. This definition was taken from Wikipedia. When we talk about informing someone, we mean that they have acquired knowledge through communication about something or someone. Claude Shannon had a question similar to that of how messages are transmitted through a communication system where a sender produces a message that the recipient receives through a communication channel. In 1948, Shannon published a groundbreaking paper on this topic titled A Mathematical Theory of Communication. This marked the birth of information theory, and for this reason, Shannon is referred to as the father of information theory. However, this episode will not delve into the world of communication systems and information transmission. Rather, we are interested in the concept of information in a very general context. But the mathematical formalization of this concept has its origin in the prior mentioned paper. But before diving into the math, let's try to build up an intuition of this rather abstract concept. Suppose we have a fair coin with heads on one side and tails on the other. If I would flip this coin, on which side would you bet your money on? Well, since both are equally likely, you will probably have no preference. Now, let's exchange the fair coin with an unfair coin that has a probability of 0.6 to land on head and 0.4 on tails. On which side would you bet now? You would definitely bet on head, since it's more likely. What is the difference between those two scenarios? In the first scenario, we were much more uncertain about which side to bet on. In the second scenario, it was pretty easy for us to decide on which side we would bet. We were less uncertain about our choice. In the context of information theory, uncertainty and information are intimately related to each other. They are essentially the same. This can be understood in the following way. In the second scenario, we would be less surprised when our coin would show heads. Thus, the information gain would be less than in the first scenario, where we would be more surprised about the same outcome. Another important observation is that we only talked about probabilities. No other factors involved. So information can only depend on the probabilities involved. Shannon argued that the information function I, which quantifies the information content of a discrete random variable x, has to exhibit the following characteristics. The first requirement is I has to be continuous on 0 to 1. Since I depends on the probability p, it has to be continuous in p. The second requirement is that there should exist a positive constant, which is being greater than 1, where the information content evaluated at 1 over d should be equal to 1. This is essentially fixing the normalization. And the third requirement is that if a choice is broken down into sub-choices and both are independent, then I should be additive in the following sense, that the information content evaluated at p times q should be equal to the information content evaluated at p plus the information content evaluated at q. A function that fulfills these requirements is the following. It's minus the logarithm of x. Note that you do not have to use the base 2. But base 2 is a conventional choice in information theory since we can relate this quantity to a number of bits. The actual unit of I is referred to as Shannon. This unit is quite handy since bits can actually only come as integers. So let us see if these three requirements are really fulfilled. So for the first requirement, that the information content function I should be continuous on the interval 0 to 1, we will not prove that the log function is a continuous function, but if you're interested in the derivation, every good calculus book has one. But let me mention one subtlety, because we said that the logarithm should be continuous from 0 to 1. Normally, the logarithm is only continuous and well-defined for x being greater than 0. It is not defined at x equal to 0. But in information theory, we often choose another convention, and that is that the logarithm of 0 should be equal to 0, such that the logarithm is continuous in 0 to 1. And as I said, every good calculus book has a derivation where one can show that the logarithm is a continuous function for x being greater than 0. Let me write down for the first requirement this subtlety, which I mentioned, that the logarithm of 0 should be equal to 0. So remember that, that's a quite important point. So for the second requirement, we just simply choose d equal to 2. And if we calculate the information content of 1 over d, what we get, so we substitute it into our formula, so it's this expression, and if we just put in for d equal to 2, we see that this is simply 1. And for a third requirement, this is also quite easy to show. So this is minus log 2 p times q. And now we just use a property of log function that we can write it as this. And this is exactly ixp plus ixq. So we really see that these three requirements are really fulfilled by our function. So let's come back to our two-coin scenarios. Let's compute the information content of head and tails in both scenarios. Let's start with the first scenario, where when we evaluate the information content on heads and tails, it will be equal to 1 Shannon, because minus the logarithm in base 2 of 1/2 is 1. Each outcome, heads or tails, has as expected the same information content of 1 Shannon, since both are equally likely. In our second scenario, we had an unfair coin, where the probability of landing on head would be 0.6 and on tails 0.4. Since head is more likely, the information content will be lower, since we are less uncertain about its outcome. This agrees with the observation we made before, where we said that we will bet on head, since it's more probable. But in both cases, the information can be encoded in 1 bit. Since head could be encoded as the 0 bit and tails as the 1 bit, the difference is just how often a bit value occurs when we would throw the coin, let's say, 10 times. So it would be nice to know how informative an outcome is on average. And this leads us to the next concept of entropy. I think you already know who adopted the idea of entropy to information theory. Of course, Shannon. The concept of entropy originated in thermodynamics and statistical physics, and was later adopted by Shannon for information theory. In statistical physics, entropy relates to the number of possible configuration states of a system. Let's translate it to our coin example. When we flip one coin, how many possible configuration states do we have? Configuration states are just a set of outcomes. In this case, of course, 2. When we throw our coin n times, how many possible outcomes could we observe? To the power of n, of course, because the coin flips are independent from each other. Each coin flips has 2 possible outcomes, so we just multiply 2 times n, 2 n times, which is 2 to the power of n. What would be the expected information content when throwing a fair coin n times? Well, therefore we have to define an expectation value for a discrete random variable x, which is exactly this expression which you can see on this slide, which is the sum over the I equal to 1 over 2m, which is the set of possible outcomes from px evaluated x times x, where x in capital letters refers to the discrete random variable x, and the smaller x is the outcome I forgot here to write down the index I. Actually, it should be px of evaluated at xi times xi. When we substitute x with information content, we just have to substitute it in, and what we get is that the expected value is then equal to minus, and we sum over the possible set of outcomes, pi times log base 2 of pi, which is also very often denoted as h of x. So this expression is called Shannon entropy and quantifies the average information content of a discrete random variable x. So we have defined the expectation value of the information content for a discrete random variable x. Let's apply this formula to our fair coin thrown n times. So what we simply have to do, so we have h of x is equal to minus, and we sum over j equal to 1 to n, and from I equal to 1 to n for pi logarithm base 2 of pi. And since our probabilities do not depend on the index j, since every event is independent from each other, we can just write it as n, and then we write down our sum. M is equal to 2 because we have only 2 possible outcomes, right? We have only heads and tails. And this will give us plus n, because this can be written as 1/2 log 2 1/2 plus 1/2 log 2 1/2. And this is equal to log 2 1/2, right? Because we can write it as 2 and the 2's cancel. And so we get this is -1, and this -1, the minus sign cancels with this minus sign here, and we get n. And what it does mean is that we need n bits in order to encode a fair coin which is thrown n times. So this also means that if we throw our coin only once, then we only need 1 bit. And how does the result differ if we apply it to our unfair coin example? So in our unfair coin example, we also have to sum from j equal to 1 to n, and also from I equal to 1 to 2, pi log 2 pi. It's the same formula, but this time we plug in other values. So we have 0.6, logarithm 2 of 0.6 plus 0.4, logarithm of 2 from 0.4. And what we get, this is approximately 0.97 n. So for one coin throw of our unfair coin, we would get an approximate value of 0.97. Since this scenario is less informative on average, the value is also lower than in our first scenario. We can extend our findings by continuously computing Shannon's entropy for the whole range of probability values, and the plot will look like this. So as we can see, we have the Shannon entropy on the y-axis and the probability on the x-axis. So what do we see on this curve? We can see that this curve is parabolic and has its maximum at p equal to 0.5, where the most uncertainty is exhibited by our coin scenario. When we decrease the probability p, then 1 minus the probability has to grow. Thus, one outcome will be more likely than the other. The Shannon entropy decreases. The same applies when p becomes larger, because then 1 minus the probability becomes then lower. If p is equal to 0, then one outcome has to come with full certainty, and one outcome will never come, and vice versa for p equal to 1. I like this plot because it shows how Shannon's entropy relates to uncertainty in a real simple scenario. Okay, this is all I want to tell you about information in Shannon's entropy. So let's talk about data. Practitioners will tell you, if you ask them what is data, they will usually respond that data comes in various forms. unstructured data such as videos, images, or text, semi-structured data like JSON or CSV files, and structured data like tabular data. Don't worry if you don't know this classification of data, we will learn more about this in later episodes. However, I like to think about data being an abstract structure that holds information. This perspective is much more general and not bound to any specific format or structure. But let's break this abstract definition down on an example. The first example is an image. The question is, can we compute the information content of an image? The answer is no. Since this is still an active area in research, but we will try to break down why it's so difficult to compute the information content. We will see that information is a very tricky concept when applied to data, since data does not consist of only bits, but exposes an internal structure. So as a warm-up, let us compute the number of pixels of a full HD image and how many bits we would need in order to store an image without any encodings and compressions applied. A full HD image has 1920 times 1080 pixels and 3 color channels. So in total, we have approximately 2 million pixels. Each pixel can have a value ranging from 0 to 255, where 0 is black and 255 is white. So 256 values in total. This corresponds to 8 bits or 1 byte. Since we are dealing with an RGB image, so with 3 color channels, red, green, blue, we need 24 bits for 1 pixel. Therefore, we need 6.221 megabyte in order to store our image. So what is now the information content of an image? It depends on the question we are asking. For that, let us have a look at 2 strategies with which we could come up with. So let's talk about our first strategy. If we would write an image as a flattened array of bits, and we could count the number of 0 and 1 bits, and from that we would estimate the probabilities for each bit, and then compute the Shannon's entropy, we would get a value in the order of 1. But this would completely neglect the fact that these bits are grouped in bits of 8 to represent a pixel value. So these bits are not independent from each other, and thus our previous computation is nonsense. So another idea could be to count the pixel values itself and estimate the probabilities that are associated with each pixel value from 0 to 255. But this neglects the fact that these pixel values are not independent from each other, but that they exhibit a structure. So as you can see, it is not always so easy to compute the information content. Alright, until now we talked a lot about information and data, but since we are interested in the intelligent systems when talking about AI, we would also like to know what is knowledge. And let's make an example in order to demonstrate what knowledge could be. In order to understand knowledge, let's turn back to our beloved unfair coin example or scenario. Suppose we are the player and there's also a dealer which asks us each turn on which side we want to bet. The dealer will throw the coin 6 times in total. We don't know that the coin is unfair and assume that it is fair. How often will we be right on average if we assume that the coin is fair? 3 out of 6 times. What we don't know is that the dealer starts with an unfair coin that will always show heads, and then exchanges the coin with a fair coin for the other turns. After a few games, we notice that the first outcome is always heads, and so we start to bet on head at the beginning of every game. How often will we be right now on average? Well, 3 to 4 out of 6 times. What we obtained is exactly what we will refer to as knowledge. Knowledge is information that the player received, such that the player can reduce its uncertainty about the environment, or more specifically, about the outcomes in this specific scenario. So thanks for tuning in for this episode. In the next episode, we will finally start with machine learning. To be more specific, we will start with error-based learning and train our first model. If you have understood the concepts that we have discussed during the last 3 episodes so far, when learning about machine learning will be natural to you. See you in the next one.